Our next speaker is Melissa Sherman Bennett, and she will talk about the hypersimplex and the m=2 amplituhedron.
Yeah, so thanks so much to the organizers for this opportunity to speak. I'll waste a little bit of time so people can come in and take their seats. Yeah, so what I'll be talking about today is joint work with Matteo Parisi, who's a postdoc at the IAS, and Lauren Williams, who's at Harvard. Our paper is on the archive if you want some more details. And I'll be talking about these two objects, the hypersimplex and the m=2 amplituhedron, and their, to me, still very mysterious connection. And actually, before I define these two objects, I have to define a third, which luckily, actually, Sarah already kind of covered. So I will go through all of my background again, just in case you didn't catch it the first time. But if you're feeling sleepy for this first slide, you can kind of sit back and relax because you've already seen most of this in Sarah's talk. Okay, so this object in the background I need to define is the totally as in Sarah's talk, if I take a point in the Grassmannian, so one of these k-dimensional subspaces, I usually prefer to think about a representative matrix for this subspace. So that's just some full rank k by n matrix whose row span is precisely the subspace I'm looking at. Okay, and I still have these Pluker coordinates indexed by k element subsets of 1 through n. So pick one of these, call it I, and just like in Sarah's talk, the Pluker coordinate pi of v is just the maximal minor of a representative matrix for V that's located in column set I. Okay, and so just to be very concrete here, maybe the representative matrix I pick looks like this, where A, B, and C are some real numbers. Then the Pluker coordinates say P14, I compute by looking at the first column and the fourth column of this matrix and taking the determinant of that square submatrix. So I would get C as P14. Okay, so I care in particular about a subset of the Grassmannian, which is called the totally non-negative Grassmannian, or TNN Grassmannian for short. This was studied first by Lustig and then later independently by Postnikov, who used very different language. They actually didn't realize that their definitions coincided for quite a while. I'll give you Postnikov's definition. So the TNN Grassmannian is just all those points in the Grassmannian with non-negative Pluker coordinates. Okay, so kind of what you would expect. And what you don't see immediately from this definition is that the TNN Grassmannian has a lot of very beautiful combinatorics, which Sarah discussed. This was mostly, the study was initiated by Postnikov, and then kind of many, many other people have contributed over the years. So I can't talk about most of the combinatorics of the TNN Grassmannian, but what I care about in particular is that it has a very natural stratification, which is topologically very well behaved. So this stratification is according to which Pluker coordinates are 0 and which ones are positive. So to be a little bit more precise, pick M, some collection of k element subsets. And this M indexes a stratum SM in the TNN Grassmannian, which consists of all points where Pi is positive if and only if I is in my collection M. So M is telling me precisely which Pluker coordinates are positive, and then all other Pluker coordinates must be 0. Okay, and okay, so to give an example, so what if I want the stratum indexed by all 2 element subsets of 4, except for the subset 1, 2. Okay, well, this stratum is all of those points with representative matrices that look like this, where A, B, and C are positive real numbers. Okay, because you can look at this matrix and you can check, oh yeah, so the Pluker coordinate P12 vanishes, all of the other ones are positive, and in fact, all matrices satisfying those Pluker coordinate conditions can be written in this way, or all subspaces satisfying can be written in this way. Okay, so of course, if you pick your collection M poorly, this stratum will be empty, so we throw those away. If the stratum is non-empty, M is called a positroid, which is a word that came up in Sarah's talk. This is a portmanteau of the words positive and matroid. And for those in the audience who know matroid theory, these strata are just matroid strata intersected with the TNN Grassmannian. Okay, and we call the stratum SM a positroid cell. And I haven't made a mistake here switching from saying stratum to cell. These really are cells, so they're homeomorphic to open balls. And okay, so like I said, kind of by definition, the TNN Grassmannian is a disjoint union of all of these positroid cells. And actually it's an even better situation than that. This decomposition is a regular CW complex, which is just means it's topologically very nice. That's a result of Galatian Karp and Lamb. That won't really matter for this talk. It's just, I want you to know that the object in the background here is kind of as nice as one could hope for it to be. Okay, so the two objects I will focus on for the remainder of the talk are images of the TNN Grassmannian under two different maps. And I apologize, this is actually a very unfriendly way to define the hypersimplex, but I'm doing it this way for the sake of analogy. So I will try to insert friendlier comments in the middle. Okay, so we're going to be considering two different maps. Let me start on kind of the combinatorial side where we have the moment map. This was studied probably not first, but definitely famously by Gelfand, Goretzky, McPherson, and Serganova. And what exactly the moment map is not so important to us. So I'm just going to tell you, it's a map from the Grassmannian into R to the N. There's some formula which we won't actually care about. And the image of the TNN Grassmannian under the moment map is called the hypersimplex, denoted delta k plus 1n. Okay, so like I said, very unfriendly way to define the hypersimplex because it's just a polytope. There's an example here. Yeah, so let me tell you some friendlier facts about it. So it's just a polytope. It has dimension n-1, so it sits inside of some hyperplane in R to the n. And I can even tell you its vertices. The vertices of delta k plus 1n are just all 0, 1 vectors with exactly k plus 1 ones. So this is a very, very concrete polytope. Okay, so that's one side of the picture. On the other side of the picture, we're going to be looking at the oh yes, I'm sorry. So EI, so sorry, yeah, there's two different EIs. So E1 down here is just the standard basis vector. And then if there's a subscript with two things in it, then that means the sum of those standard basis vectors. And same thing up here. So I is a subset, a K subset. So yeah, this is a sum of K standard basis vectors. Okay, so on the amplituhedron side, we have a different map called the M=2 amplituhedron map. And to define it, I first need to pick a helper matrix Z. So this will be an n by k plus 2 matrix with positive maximal minors. Okay, and given such a matrix, it induces a map between two Grassmannians by matrix multiplication. So how does this map work? Well, I start with some point in a TNN Grassmannian, say it's represented by matrix A. Then I just map it to the point in a different Grassmannian represented by the matrix A times Z. And this matrix A times Z really is full rank. So it does, and it's K by K plus 2. So it really does give us a point in the Grassmannian GRK K plus 2. Okay, so there's some map. If I take the image of the TNN Grassmannian under this map, Z tilde, then I get the amplituhedron. Okay, so what is this thing? Well, before I tell you why it was defined, I will warn you that the hedron in the suffix is very misleading. It's kind of just wishful thinking. This is not usually a polyhedron. I've drawn an example kind of in the only circumstance in which it is a polytope. So the example is also misleading. Yeah, so let me say this is not a polytope. And it's full dimensional inside of its ambient Grassmannian. So it's 2K dimensional. Okay, so yeah, go ahead.
So just to make sure, the amplituhedron is independent of the choice of the matrix Z?
Very good question. It's not. So basically, physicists can think that all of the properties of the amplituhedron they care about are independent of Z. Yeah, but actually in the course of this work, we discovered some things that do depend on the matrix Z, and we were pretty surprised. They sort of don't interfere with what the physicists care about, but yeah, it's sort of a very good question. Okay, so why did the okay, so yeah, so I've already revealed the amplituhedron is of interest to physicists. It was defined by Arcani, Hamid, and Trinka, who are physicists who care about, among other things, scattering amplitudes. So Hugh mentioned these in a sort of different context. So I'll give my version of the story. It's mostly a lie because I'm not a physicist, but this is how I think of it. So scattering amplitudes are functions that predict what happens when particles are zooming around at high velocities and maybe they smash together and scatter into new particles. And the idea behind the amplituhedron is the volume of the amplituhedron is a scattering amplitude. So volume is in air quotes because it's not actually the volume, it's just something that behaves kind of like the volume. So that's what you should think of it as for this talk. But yeah, so physicists want to compute the volume of the amplituhedron because it solves one of the problems they're interested in. It produces for them a scattering amplitude. Okay, so remember the TNN Grassmannian has this nice decomposition into cells, and we will also care about images of cells under these two maps. So let me give some notation. So if I take the moment map image of a positroid cell closure, I get a polytope sitting inside of the hypersimplex called a positroid polytope. And this is my notation. And again, there's a nice description of positroid polytopes that doesn't involve the moment map at all, which I'm not going to give you, but there is one. It's really straightforward. On the amplituhedron side, if I take the Z tilde image of a positroid cell closure, I get, well, what I'm denoting by Zn, I'm going to call it a grasstope, which is a portmanteau of Grassmann and polytope. Again, it's not actually a polytope, whatever. This is language of Thomas Lamb. Okay, and here's an example. Again, these are only polytopes for the k=1 case, which is what I've drawn the picture of. So M indicates the positroid cell. I'm sorry, I can't quite hear you. It's the cell. So it's the positroid cell indexed by the positroid M or N. Okay. Okay, so for combinatorialist, kind of all positroid polytopes feel equally worthy of study. But for a physicist, not all grasstopes are equally interesting. So they care particularly about the grasstopes which are full dimensional and have easily computable volumes. And that's because they want to compute the volume of this amplituhedron. And what's one way to compute the volume of a big object? Well, you slice it up into smaller full dimensional pieces and you compute the volumes of those and then you add it up. So physicists care particularly about particular grasstopes I'm going to call amplituhedron tiles. And these are the grasstopes that are full dimensional, so 2K dimensional, and such that the Z tilde map was injective on the positroid cell Sn that the grasstope comes from. And the reason that they like these is because apparently they can compute the volume of positroid cells, and then if the Z tilde map is injective, then the volume kind of isn't being disturbed by the Z tilde map. Okay, and so just blindly, I can make an analogous definition on the hypersimplex side. So a hypersimplex tile is a full dimensional positroid polytope. So now these are n-1 dimensional, such that the moment map is injective on that positroid cell Sm. And kind of as is the theme on the hypersimplex side, I can actually give you a much nicer definition of hypersimplex tiles. These are actually just the smallest full dimensional positroid polytopes. So smallest in the sense of there is no other full dimensional positroid polytope contained inside of these. Okay, so I'm gonna keep plowing forward with my analogy. So physicists also, right, are of interest to physicists are things called positroid tilings, which are basically exactly the sorts of decompositions you need to compute the volume of this amplituhedron. So a positroid tiling is a decomposition of the amplituhedron into tiles with disjoint interiors. Okay, and right, because the tiles are the pieces whose volumes we know, and if we want to compute the volume of the big thing, we should definitely break it up into pieces that don't overlap. Okay, and again, I can just blindly make exactly an analogous definition on the hypersimplex side. a positroid tiling of the hypersimplex is some decomposition into tiles with disjoint interiors. Okay, and at this point you might be thinking, well, yes, you can define a bunch of things in analogy to something physicists care about, but why should we care about it? And the answer is, well, okay, so the notion of tiling is kind of weak if you usually think about decompositions of polytopes. You might be more used to thinking about like polyhedral subdivisions, or in particular regular polyhedral subdivisions. And so the answer I'm going to give you for why you care about positroid tilings is because there is a subset of them which are just regular polyhedral subdivisions. So this is where the boundaries of all of the tiles interact in a nice way. And that set of positroid tilings, which are regular polyhedral subdivisions, is parametrized by a very nice mathematical object called the positive Dressian, which is of independent interest and was studied recently by Spire and Williams and independently by Arkani, Hamid, Lamb, and Spradlin. So let me just write down. The reason to care about this is maybe the positive Dressian. Okay, and I'm not going to tell you what the positive Dressian is, but it is a polyhedral fan, and its maximal cones correspond precisely to these positroid tilings, which are regular polyhedral subdivisions. So the takeaway from this side is there's a special subset of positroid tilings of the hypersimplex where we have some understanding of like a global structure to the tilings because we have some object in the background which is parametrizing them. Okay, so why have I taken a very long time to define these two things in analogy? Okay, so I will not keep you in suspense. So the reason I've done this is because of a conjecture of Lukowski, Parisi, and Williams. So they define a particular bijection called T-duality, which they conjecture is a bijection between the positroid tiles for the hypersimplex and the tiles for the amplituhedron. And so, okay, so I'm not going to tell you what this bijection is, but I will tell you it's defined on the level of the positroids indexing the tiles. So it's not a geometric map, it's a combinatorial map. And it takes one positroid M to another positroid M hat. And I'm going to call gamma M and ZM hat T-dual objects. Okay, so they define this map. They conjecture that it's a bijection between hypersimplex tiles and amplituhedron tiles. And then they further conjecture that this T-duality induces a bijection on the positroid tilings. Okay, so the first statement is saying something like the good behavior of the moment map on positroid cells matches up in some way with the good behavior of the Z tilde map on some other positroid cells, which is like a very surprising statement because the moment map and the Z tilde map seem to have very little to do with each other. And you know, these objects are different dimensions, they live in very different ambient spaces, et cetera. And then the second point is saying that, I mean, this bijection is like the right one because it also has this nice property on the decompositions on the two sides. Yeah. Yeah, so I'm not actually sure about that. I was asked, is this statement also helpful for the volume computation? I mean, in some sense, definitely yes, because if it were true, it would give you a bunch of amplituhedron tilings, which you didn't know existed before. And so that would definitely help you compute things. In terms of like, can I take some volume statement on the hypersimplex side and translate it? I don't know. So this is where it becomes important. It's not actually a volume, instead it's some differential form. Okay, so yeah, so maybe I can say why it would be attractive to have a statement like this. So one thing is just, it's very weird. It's kind of nice to prove weird things. I don't know, it gives you hope that there are like things yet to discover. Another reason why it's helpful to have things like this is because, well, as you probably noticed, when I was doing the hypersimplex side and the amplituhedron side, I knew much more about the hypersimplex side. I could give you really nice explicit descriptions of everything that was going on without mentioning the moment map. And I really couldn't do that on the amplituhedron side. I had to mention kind of just the definition in terms of Z tilde all the time. So something like this, you would hope would let us kind of port some results just from kind of the convex polyhedral geometry side into this non-polyhedral side. Yeah, and the other thing I'll say is they give some support for this conjecture. Yeah, so they verify that each each hypersimplex tile is an amplituhedron tile, but then they're not sure if there are more amplituhedron tiles. And they also show that a certain class of positroid tilings for the hypersimplex is taken to a positroid tiling for the amplituhedron by the T-duality map. Okay, so the results I'm going to tell you about today is that this theorem is true. So there is a bijection between positroid tiles on the two sides, and it's given exactly by this combinatorial map T-duality, taking M to M hat. And it induces a bijection on the positroid tilings. And we give a bit more. It's quite a long paper, but among other things, we also give for the first time an inequality description of the amplituhedron tiles. So we give a definition that doesn't have anything to do with the Z-tilde map. We just say it's a subset of GRK K+2, which is cut out by these inequalities, linear inequalities in Pluker coordinates. Another thing we do is we kind of beef up this mysterious connection between the amplituhedron and the hypersimplex by showing there's even a finer decomposition of the amplituhedron you can take, which is in some sense T-dual to a classical triangulation of the hypersimplex. But it's kind of at the level of combinatorics where we can like match up the pieces in a very nice way. We don't have still a geometric map between the pieces. Okay, so let me take my last few minutes to try to tell you a bit more about these results, see how far I get. Okay, so how do we show this bijection between positroid tiles? Well, we show that both sets are in bijection with a different set of combinatorial objects. And the combinatorial objects in question, pictures that look like this. So they're properly bicolored subdivisions of an n-gon with area K. Okay, so a subdivision of an n-gon means I've taken an n-gon and I've laid down some diagonals to break it up into smaller polygons. The properly bicolored part means I've colored things, the smaller polygons black or white, so that no polygons of the same color share an edge. And this area statistic is just telling me how much of my polygon is covered in black, basically. Okay, and so from such a picture, I can read off both M and M hat. And so this is kind of, yeah, this is how we prove that T-duality gives the bijection. Okay, and so what's very nice about this picture though, these properly bicolored subdivisions, is they give us even more information about the positroid tiles. So the way this works is, if I pick any non-crossing diagonal, so any diagonal that doesn't cross the arcs of my subdivision, so say this one, this arc will give me two linear inequalities, one satisfied by the hypersimplex tile and the other one satisfied by the T-dual amplituhedron tile. And so of course these inequalities can't be the same because the hypersimplex tile sits inside of Rn and the amplituhedron tile sits inside of GRK K+2. These are different dimensions. They have like different looking coordinates, et cetera. But what's very nice is that the bounds on these linear inequalities, so like the number on the right-hand side, it's derived from exactly the same combinatorial statistic on this picture. So this is not like it's still not a map from this positroid polytope to this grasstope, but it is some connection between their geometry. Yeah, oh, and I put this, so this is the numerology in case you're interested. So this is the number of positroid tiles for the amplituhedron or the hypersimplex, refined by N and K. And I think this is a refinement of the large Schroeder numbers. This also counts separable permutations with precisely K descents, or maybe K-1, I can't remember. Probably K, because I don't want -1 descents. Okay, yeah, so if you're interested in these numbers, here they are. Okay, so that's it about tiles. And now for the tiling result, I don't really have time to tell you much of anything, so let me just illustrate it and give you like one sentence about the proof. Okay, so here is, okay, so our result again is that this map T-duality induces a bijection between positroid tilings of the two spaces. So how it works is I take some positroid tiling of the hypersimplex. It consists of two tiles, the blue polytope and the green polytope. I take each of them and I consider their T-dual grasstopes. So that's the blue guy over here and the green guy over here. And the T-dual grasstopes form a positroid tiling of the amplituhedron, and it works backwards. And all I can say about the proof is that we do this by taking the simultaneous refinement of all positroid tilings on both sides. So that slices both of the objects into smaller pieces, and then we match up the pieces. And the point is that also this is like a good decomposition. So if on one side a small piece sits inside of a tile, then on the other side, the T-dual small piece will sit inside of the T-dual tile. So it's kind of a way, yeah. So it just gives us a way to connect the tilings on the two sides. And this, I don't have time to say anything about it, but this is actually where we see the dependence on the Z matrix is some of the subtleties of this argument. Oh yeah, and I should also say the simultaneous refinement of all positroid tilings on the hypersimplex side is actually just a triangulation studied first by Stanley, then Sturmfels, and then by Lamb and Posnikov, all kind of in different language. And the maximal simplices in that triangulation are enumerated by the Eulerian numbers. So they correspond to permutations with maybe k-1 descents, something like that. And so on the other side, on the amplituhedron side, that's also what our chambers are enumerated by. So they're in bijection with permutations of maybe n-1 with k-1 descents. Okay, and that's all I've got. Thanks so much for listening.
Thanks so much. Any questions?
That's a lovely talk. I was hoping you were going to come back to the volume point, though, in the beginning. Your kind of air quotes, the volume of the amplituhedron is the scattering amplitude. So can you, now that you've got this lovely bijection, does that help you go back and answer the volume questions?
Yeah, so I think it doesn't. So I can't, there's some physics papers about defining an analogous differential form on the hypersimplex side and kind of checking to see if it gives you the right thing. I sort of think, well, they don't study exactly this question. They look at an analogous object called the momentum amplituhedron instead of the amplituhedron. And in that setting, the answer is kind of no. The differential form they define, which maybe is the wrong one, who knows, it gives you different answers depending on which tiling you pick, and that's very bad. Yeah, so I'm not too sure about the differential form. It would certainly, like, maybe there's like another question more for mathematicians, like there's a perfectly reasonable notion of volume for the hypersimplex. So now maybe we should think about volume in the like normal mathematical sense in the amplituhedron. And I've never thought about that, but it might be very interesting.
Thanks for the talk. It was very, very good. So for the facets of a positroid, there's usually an associated cyclic flat, which for positroids is an interval. What does this cyclic flat tell me to the corresponding inequality of in the amplituhedron side?
Yeah, so okay, so I think what you're asking about is like on the positroid polytope side, the way I get the facets is I look at the edges of my black polygons, and then each one of those gives me a facet defining inequality for the positroid polytope. Is that what you're?
Yeah, well, I'm not sure how the relationship goes with the particular bicolor diagram, but I just know matroids, their facets, their inequalities correspond to cyclic flats.
Yeah, so the facet inequalities are like, one of the facet inequalities looks like this. So I think 2 through 4 is probably a cyclic flat. On the amplituhedron side, there's an equation which also involves that cyclic interval and also gives a facet of the amplituhedron tile. So there's a, yeah, so probably the cyclic flats of the positroid probably correspond to facets of the amplituhedron tile. And I'm not totally sure because I would need to sit down with you and figure out exactly what the cyclic flats are, but yeah, I think that's probably true.
Great talk. Is there a version of T-duality for when m is not 2, like other values?
Yeah, it's you just compose the current T-duality map a bunch of times. So yeah, the amplituhedron is only studied for even m because odd m seems to be pathological. And so yeah, you always do the T-duality map m over 2 times. And that's supposed to be T-duality for bigger M.
Okay, cool. Thanks.
Okay, let's thank the speaker again.